Good morning, and thank you for giving my colleague Jeff Nguyen and myself the opportunity to perform this analysis and forecasting for your investments portfolio. Overall, we analyzed 3,202 publicly traded stocks on the NASDAQ from a 100-day daily time period between May 30th and October 30th, 2019. We selected this time range for its distance from unusual market disruption in order to develop a proof of concept model that can be enhanced for different deployment conditions. The forecast horizon we selected spans 5 data points, representing 1 trading week. Because of the time constraints involved with directly analyzing each stock's time series, we developed a loop to iteratively process through and perform a linear model on each stock where the slope of price is positive to isolate profitability. We then quantified frequency values in the power spectrum to identify consistent wandering behavior based on a peak at 0 with no additional peaks thereafter. This method allowed us to identify 7 stocks ideal for signal plus noise modeling. From these stocks, we selected one and modeled it. Because we have high, low, open, and close prices, we wanted to visually inspect the relationship between these across all data points once we selected the stock to model. Through this visual assessment, we identified differing amounts of variation within each price set across all data points. As a result, we decided to engineer 2 new features to capture this variation. These 2 new features allowed our multivariate modeling to parameterize additional insights for forecasting development. In this signal plus noise model, we perform a hypothesis test on the linear trend using both ordinary least squares and the Cochran-Orcutt test to conclude the signal is not random, but rather deterministic trend. We next removed the residuals from the trend line and built a model for this data. We then tested those residuals for white noise variance using the Young box test, which indicated there is not enough evidence to differentiate the residuals from white noise. Because of the stationarity of the residuals, we were able to estimate a model using the linear slope and the variance of the residuals. Forecasting error was measured in terms of average squared error using the last 5 data points. Within the data, we identified only one 1 minus b factor, which is not enough for ARIMA to forecast a trend to continue, but is enough to justify differencing the data. Through applying this difference, we were able to stationarize the data and then build an autoregressive moving average model. We identified an AR5 component based on AIC. While this was not the top selection using AIC, we tested several lag orders and determined this is the best fit since there is not enough noise in the data to fully justify it including an MA term, but enough to still model. The residuals produced a Young box p-value of 0.94 with k equals 24 lags, high enough that we could not reject the null hypothesis. We therefore concluded that the distribution of the residuals are close enough to white noise that we cannot effectively distinguish the difference. Low variance and a residual AIC suggesting an ARMA 00 further aided in concluding the model is well fit. We forecasted using an ARIMA 510. Following the univariate modeling of this time series, we enhanced our model with multiplicative parameters. Here we included our engineered features as both additive and multiplicative terms to aid in explaining and forecasting the series. Our vector autoregressive model with additive terms for trend, volume, the spread between high and low, and open and close prices, in addition to a multiplicative term for trend and its impact on volume, outperformed all other VAR models we built in terms of ASE. The autoregressive order identified for the model is an AR2. A multi-layered perceptron operates using a feed-forward artificial neural network to pass information from the input nodes into a hidden layer of nodes that perform logical activation functions before processing into the output node. When adding additional predictor variables to the multivariate models, the forecasts converge less toward the long-run mean and more toward the behavior of the realization itself. Therefore, the addition of useful predictor variables, such as those from natural language processing for sentiment analysis, can aid in further stabilizing useful multivariate models. When we added a multiplicative term for trend and volume to the NLP, our ASE dropped to 0.6, our lowest of all models. This model includes 2 univariate lags on the univariate input nodes with 4 exogenous regressor lags across the regressor nodes. When comparing all candidate models, the model with the lowest fixed ASE is the MLP, while the model with the lowest 5-point windowed rolling ASE is the signal plus noise. Therefore, we selected the ensemble between these as the best for forecasting. This ensemble provides the flexibility of using multiple predictors while also maintaining a lower risk of overfitting provided by using the univariate signal plus noise. As mentioned, we selected the ensemble model for its low forecasting ASE and its ability to resist overfitting from including too many predictors that can change in value very quickly to negatively impact the forecast. The best model by ASE is the MLP, while the best model by 5-point windowed rolling ASE is the signal plus noise. Together, these produce our ensemble. Displayed here are our competing top models. Displayed here are our top 2 models, the MLP and the ensemble. Thank you for your time today. Should you find our models appropriate for your business needs, please feel free to contact us through our company email through which we have arranged this meeting,